Hello everyone, this is Dr. Webb. So far, since we started, working on multiple integrals, I've kind of avoided talking about applications, and the reason for that is that, to me, in my mind, most of the applications really make the most sense once you get to three dimensions. And so I've kind of been putting it off until we got to triple integrals, but now we're here at triple integrals, and so this seems like a good place to do it, and one that's really that is very easy for us to picture and visualize is mass. And so I thought we'd do some applications involving mass using triple integrals. Okay, and so if we're thinking about this in three dimensions, if we have some solid, we want to talk about we want to have what's called a density function. And so this is the delta of xyz, and this is telling us what the density of the solid is at each point inside. Okay, and so if you recall, when you first probably learned about density in grade school, what's density equal to? Well, it's the mass of something divided by the volume. And so this is the originally when you thought about this is you're thinking about what the something with a constant density, so the density at every point is the same. Well, to figure out what that density is, you take the mass of it and divide by the volume of it. Even if you use this same formula of taking the total mass and dividing by the volume, then this density that you're going to get right here, this is going to be the average density. Okay. So for our purposes, we're going to sort of imagining inside of S, focusing in just on little bits of volume, and assuming that on that little bit of volume, the density is essentially the same. So we're going to go and think about delta V. This is going to be the little bit of volume. And delta M is going to be the little bit of mass of that volume. So this is the mass of the little bit of volume. Well, so if we know the density at that point, let's call it the density at that point, let's say that it's at x naught, y naught, z naught. Right. Well, this density is going to follow this formula. It's going to be the mass over the volume. Well, if you're looking at this, we have our function for density. We know how to deal with little bits of volume, and we're trying to learn about the mass. And so it makes sense to solve for delta M if we're trying to get the mass out of this. So we can do that. Delta M is going to be equal to the density at the point times the little bit of volume. And again, we're assuming that the density is essentially constant over this volume. And so this holds true. And now this looks like something that we can use a Riemann sum for. And so when we take the Riemann sum on both sides, really deep down we end up integrating. So we're doing this in three dimensions. Our density, and delta V turns into dV over the entire solid. What's this going to give us on the other side? Well, we'd be integrating all the little bits of mass. So this is really dm over the whole solid. Well, if we add together all the little bits of mass over the whole solid, what do we end up with? This is the total mass. Okay. So to get the total mass of a solid, if we know its density at each point, we just integrate that density over the volume, and that spits out the total mass. Okay, so this is our formula on how to get mass, given our density function. And so this M here is representing the mass of the solid, the mass of S. Okay. As a little aside, what if we had our density was 1 everywhere, right? So our mass would be the triple integral of 1 times dv, right? So we'd just be integrating dv. Okay. On the other hand, this is now something of constant density, and so we know that mass over volume is going to equal 1. And so if mass over volume is equal to 1, that essentially means mass and volume are equal, at least numerically equal. And so if this is mass, then this is also volume. Okay. So this gives us a formula if at any time we're just integrating dV over a solid S, that's giving us the volume of the solid. So formula for volume, volume is the integral of dV over the solid. And this actually, there are analogs to this in other dimensions. So in one dimension, length, this is kind of silly, but if you want to know the length from x1 to x2, you could just integrate dx between them, right? And this will give you x2 minus x1. What about in two variables? So if you take a region and just integrate dA, what's this going to give you? Well, the analog of volume and length in 2 dimensions is area. And so if you just integrate dA over R, this is going to spit back out the area of your region. Okay? And so these are some good formulas to know. This is particularly if you have some region that's kind of nasty, but you have a computer nearby and you want to figure out the area of it. If the computer can calculate the double integral of dA, then that's going to give you the area. Okay, so now let's start focusing in on, now that we have mass, let's start focusing in on figuring out the center of mass. Okay, and so we're going to do this kind of thinking about 2-point masses. And sort of the example that I always come down to, think about, get my mind straight on this, is let's imagine that there is a mathematics professor, and he is taking his child to the park, and they want to be on a seesaw together. And so here's this board is representing the seesaw. Here's the child. Clearly the mass of the math professor is much, much bigger than the mass of the child. And so where does the fulcrum, the center of the seesaw, need to be in able to allow them to actually have some balance and actually use the seesaw? Well, you're never going to get the masses on the two sides to be equal, but that's not really what you need. You just need to figure out the point where rather than the masses, you need the forces coming down to be equal. And it turns out that the forces, they're proportional to the mass, but they're also proportional to how far you are away from the center. Okay? And so the physics here boils down to, if we're going to have 2-point masses, so you can think about M1 being the math professor and M2 being the child, and they're resting on the x-axis, so the math professor's at x1 and the child's at x2, and let's assume that x1 is less than x2. Well, then the force, if C is the center of mass, then the force by the math professor is proportional to his mass times his distance away from the center. So this is mass, and this is distance from center. And you have the same equation for the second mass. The signs flip here because if x1 is less than x2, C is going to be in between x1 and x2. And so the C minus x1, this is equal to the absolute value of C minus x1, because C is going to be bigger than x1. And x2 minus C, this is also equal to the absolute value of C minus x2. But in this case, x2 is bigger, so when we take the absolute value, we have to flip the sign. And so if m1 is much bigger than m2, well, then that means that x2 minus c has to be much bigger than c minus x1 to get this balance here. And so a bigger mass would have to be closer to the center, smaller mass farther away from the center. Okay, and so this is our basic equation. And so what do we want to do? Well, we want to solve for c's here. Okay, so how do we solve for c out of this? Let's clear out some space. Okay, so we're going to solve for c here. So I get m1c minus m1x1 is equal to m2x2 minus m2c. So let's get the c's to the same side. So I have m1c plus m2c is equal to m1x1 plus m2x2. And now we can pull a c out from over here, and to get c by itself, we're just going to divide by m1 plus m2. Right? So at the end, we can get the center of mass between these two would be you add m1x1 plus m2x2, and then you divide by m1 plus m2. And one way to think about this m1 and m2, or actually an important way to think about it, is this really is the total mass of the two objects, right? Okay, so this is the basic idea, just dealing with it with 2 point masses. So from here, now we can kind of build up and think about it if we had it happening on, say, a whole line, right? And so next we're going to consider a linear rod. So think about it as being very thin, it's just long, and so really the main variable here is the length. The width and the height are really negligible. And so we're going to let delta x represent the density of the rod at x. So we're allowing this rod to change density all the way through. Okay. So if c is the center of the mass of the rod, we can do the same kind of calculation we did before on the seesaw, to think about what the force is pulling down. If we take the rod, and let's say C ends up being right here, well, what's the force pulling down at that bit right there? Well, it's the exact same idea before. If this is a little bit of the mass, we'll call this delta M. And then the force is proportional to its distance away from the center, right? So if we're using the absolute value here, because we don't know whether x is bigger than c or smaller than c, right? So, but the absolute value of c minus x, this is looking at the distance from c, and the delta M that's the little bit of mass, okay? Well, from what we saw before with density, since we have the density function, the mass is just going to be that little bit of density over the length, and so that's delta x, little delta x times big delta x. Okay, and so we're going to now that we know how much it's pulling down at each, if this is C, now we know how much it's pulling down at each little bit. Since it's balanced at C, that must mean that all the forces pulling down to the left of it have to equal all the forces pulling down to the right of it. Right? And so this gives us what I think in physics they call a balance of forces equation, which is, here it is, balance of forces equation right here. So this is looking at the forces to the left side is looking at the forces to the left of C, and so this is looking for when x is less than C, starting off at x1, and then the right side is looking at the x's that are to the right of C up to x2. And so the integral is representing the total force coming from the left side, and then the integral on the right is the total force on the right side. So these have to match up. Okay, and so if you look what we're integrating the distance from C times the density, delta x, little dx, and then on the right side the distance from C, because x now is bigger than C, the absolute value then swaps the signs, delta x. Okay, now we can use, so this is where this formula is coming from. Okay, now we can use what we know about the rules of integration now to break this up. So in all of this, we're thinking about C as being a constant, delta x as being our function, and this line is not correct. This line should be C delta x. Oh, I see what happened. There should be another C right there. Okay, so what happened here? So we can break in between these two lines. I can break this up into C delta x dx minus x1 to C x delta x dx. Same thing on the right hand side, C to x2 x delta x dx minus C to x2 C delta x dx. Okay, and so then what I'm going to do is I'm going to take these two integrals where C is inside the integrand, and I'm going to move them to the right hand side. And so that's that integral there. And then the two integrals with the x in the integrand, I'm going to move them both so they're both on the right hand side. And so that's what we have right there. Okay, and so this second line right here is coming from splitting those up and moving them next to each other. So that gives us this line with the C there. Now if you notice, this integrand matches this integrand, and the upper endpoint of this integral matches the lower endpoint of that integral. And similarly on the right hand side, this integrand now matches that integrand, and this upper endpoint matches that lower endpoint. And so what are the Calc 1 rules of integration then tell us we can do? Well, then we can combine these two together, right? So I can have it, instead of going from x1 to c and then from c to x2, I can just have it go from x1 to x2, c delta x dx. Same thing over here, x1 to x2, but now we're integrating x delta x dx. Okay, now what are we trying to get out of this? We're trying to figure out what c has to be, and c is just a constant on the left-hand side, and so we can pull it out. Okay, so let's do that. C is coming out. And now this lets us solve for c. We can solve for c by dividing out this integral right here. Yeah, so we can pull c out of there. C is equal to x1 to x2 delta x dx, which is equal to x1 to x2 x delta x dx. And then to solve for c, divide out the integral on the left. And so this is our formula for the center of mass. Right? We're going to integrate on the top. It's going to be x times delta, that should be of x there. And then on the bottom, we're just integrating just delta x dx from x1 to x2. And so this right here, this, same as before with the 2 point masses, this is the integral of the density from x1 to x2. That bottom there represents the mass of the rod. And then for the top integral, we're integrating x delta x dx, and so it's called a weighted integral, where we're multiplying by the x-coordinate times the function. Okay, so now let's make this a little bit more complicated. Let's go up one more volume, one more dimension. And so now instead of in 1 dimension we had a rod, now in 2 dimensions we can have a region, which when we think about a region with mass, the special name for that is what's called a laminate. So laminate you think of as being a region on the xy plane that has mass, and so it has a minimal amount of infinitesimal height to it, but just enough to give it mass. And so we have our R here. Looks like this. We have a density function for each point, and so we get that the mass of R, using our formula from before, is going to be integrating the density over here. Okay. Now, how do we find the center of mass for over this entire region? So the idea is, what we're really going to do is, first I'm going to find some line that's going vertically. And so if this is happening on the xy plane, this line is happening at some value, let's call cx. And I want, rather than trying to get a single point where everything balances, I'm just going to try and get it to balance over this vertical line first. And so we're looking for, we want to balance over this line, or find the right x-coordinate that makes things balance over this. Right. And so the thinking here is that for some point off of here, the force that's pulling this point down on the left, I can go back to the thinking that we did originally with the point masses. The force here is going to be proportional to this distance right here. Right? So if this is happening at x, my force pulling down at this point is going to be proportional to the mass at this point. So let's call that delta m times the distance x is from Cx. Okay. And so we have the same sort of formula that we had before. Okay. And so we want to find this value Cx, that when we take all of the forces, we calculate all the forces on both sides, it causes the laminate will balance exactly on this. And so this is actually something that you can do in real life. You know, and something when I'm live in a classroom, I really like doing this demonstration. Like I have a cardboard cutout of in a regular shape, in this case the state of Virginia, and you can kind of come up with a line that it's actually not that difficult to do. If you have a bar underneath it, you can find the line that gets the state to balance exactly halfway on. It's not, get it to balance on both sides, right? And so instead of doing this in real life, we're trying to do this mathematically to figure out what this line should be. Okay, and so we end up with the same sort of equation we have before. And so you notice R here I have broken up into R1 and R2. So R1, if this is R, RR looks different than it did before. And this looks like Cx. R1 is the region on the left. R2 is the part of the region on the right. Right? So I integrate all in the left region, and that's going to give me the same value of what I get on the right region, and that's representing that the two forces are balanced at that point. Okay? Now we can do the exact same manipulation that we did before. Even though this is written in double integrals, we still can break everything else up before exactly the same way that we did it with in one dimension. Right? And so, same as before, I'm going to erase my picture of the region. Same as before, I can take this integral and break it up into R1 C delta xy dA R1 x delta xy dA. And on the right side, break it up to x delta xy dA on R2 minus C delta xy dA R2. And again, the two integrals with the c's in them, I'm going to move them over to the same side. The two integrals where x is in the integrand, I'm going to move them over to the same side. And then, same as before, this c here should be cx, cx. Same as before, you can pull out the cx because it's a constant, and then divide by the bottom. Divide by the integral you have on the left to solve it out. And so this bottom integral here, again, is representing the total mass. Okay, and so this is giving us the x-coordinate for this line, this vertical line, where everything balances. And so here it is again. And so now we have a vertical line in which it balances on. Then we're going to repeat the process in the y direction, and this is to find a horizontal line. So c of x, this is giving us a vertical line of balance. cy, this is giving us a horizontal line. of balance. Okay, so we have an x-coordinate in which it balances on. We have a y-coordinate in which it balances on. And so here they are. And so if, again, this is our region, it's balancing on x equals c of x. It's also balancing on y equals c of y. Well, these two lines, they're going to hit at some point. That point is precisely c sub x, c sub y. And guess what? That's our center of mass. And so when I do this in class, live in class, you get two lines, and where you get you get your shape to balance on both of these lines. They're going to cross somewhere. The point in which they cross, that's the center of mass. And then you can literally balance your irregular shape by putting, essentially a single finger or one or two fingers underneath that point, depending on how precise you were marking it. And then the shape will then balance exactly on that. It's a sight to see. Sorry, I can't do it for you through this video, but if you ever meet me in person, you can see me in person. You can ask me to do this. Yeah, and in this, particularly we picked the x and y directions just because it makes the integration the easiest. It turns out that these lines, don't even have to be perpendicular. We just have to find two different lines, any two lines in which it balances on, and they always are going to intersect at the center of mass. Okay. Yeah, so that point CX, CY is the center of mass of the laminate. And so now that we know how to do this in 2 dimensions, how to do it in 3 dimensions, it's pretty much exactly the same idea. So in 3 dimensions, the integrals are going to look the same, except now we're in 3 dimensions, we're doing triple integrals rather than double integrals. In all of these, the denominators are always the total mass. And then in the integral on the top, you're always multiplying the density function by the variable in which you're trying to find the coordinate. So to get the x-coordinate, you multiply it by x. To get the y-coordinate, you multiply by y. To get the z-coordinate, you multiply by z. And the derivation is exactly the same. In this one, instead of trying to find lines in which the solid balances, it's like you're trying to find a plane where the solid balances on. And you just repeat that in each variable. Those 3 planes are going to intersect at a single point. So in this one, we're doing all of this specifically to do mass and center of mass. But it turns out that this derivation actually applies for a number of what seem to be very different ideas, very different places, but the formulas all turn out to correspond to each other and essentially be the same. And so another in particular is if you do probability. So this x bar, this represents you have a number of events, x1, x2 up to xn, and you're looking at the probability that all those events happen together. Okay, and so this is normally denoted as sort of an x bar, and this is just x bar is representing x1, x2, xn. These are all different probability events. Okay, so the density function that we saw for mass, well, it has the analogy of it is what's called a probability density. Usually they use delta the same way that we use delta for density, lowercase delta. This is the one bit of difference, is that in probability density, in probabilities, the total probability of everything happening is 1. And so this has to be, probability density functions have this property that when you integrate over the entire space, the integral has to turn out to be 1. And so when you then integrate over solids on smaller pieces, then that integral always has to be less than 1. And so if you have some S inside your total, what's called probability space, S is some subset of the probability space, then the calculation that we did for the mass of S, and so again, this was doing the triple integral of the density of x bar, say dv over S. So for what we did for mass, this was mass, it turns out that this is what gives us probability. And so this, if you do this over S, this gives you the probability that your variable will end up landing inside of S. And then even the center of mass has an analog. The formulas that we have for center of mass, this actually gives you the expected value of your variable. And so the formulas are exactly the same. The actual derivation of it exactly the same. The setup is different, but it turns out that everything else is exactly the same. So, these formulas, even though we did it for mass, they really apply much broader. And so in fact, if you think about a triple integral of some density of anything, so you can think about, say if you're taking your density is sort of representing, what the, say you're looking at the atmosphere and what the density of a particular gas is, how many parts per million of a particular gas is at different heights going up in the atmosphere. Well, then if you then integrate over the whole atmosphere, this actually is going to give you the total amount of that gas in there. Okay, that is all I have for you for this video. I will see you again soon.